Hello and welcome to the webinar on simulation and automated deep reinforcement learning. My name is Arash Mahdavi and I'm going to be your host today. This webinar is a joint webinar between SkyMind and AnyLogic. Eduardo Gonzalez, VP of Engineering at SkyMind, and me are going to be the presenters of this webinar. The first thing that Eduardo is going to show us is why use reinforcement learning with simulation models. And then we get through some overview of how reinforcement learning works and its application. Then Eduardo shows you an overview of how Pathmind works and how Pathmind is going to automate the reinforcement learning process for you. Then I come in and I show you the inner workings of the interconnected call center, which will be used as the training environment in this example or this webinar. I will show you how that model works. I'm not going to show you how to build the model, but I'm showing you how that model works, and I show you how to add functionalities that is needed to build the bridge between the simulation model and the reinforcement learning platform, in this case, Pathmind. Then Eduardo shows you how you can use a Pathmind library or Pathmind helper element, and how you add it to AnyLogic to use the functions that you built in the previous step and actually build the connection between your AnyLogic model and Pathmind before you upload it to the Pathmind cloud platform. Then you specify the reward in the Pathmind, and we show you how you can check for its convergence. Eduardo will also show you how you can run parallel experiments evaluating your deep reinforcement learning progress and how you can select the best train policy. Then you will see how to download that and implement the best train policy in your simulation or in other tools. And at the end, Eduardo will show you how you can get access to the Pathmind platform, and then I come back with Eduardo, and we will be available for Q&A. So as I said, please write your questions in the GoToWebinar field for Q&A, and we gather all of those questions and we select some of them depending on how much time we had at that point to answer them as we go. So without further ado, I'm going to switch to the pre-recorded video, and as I said, I'll come back at the end to answer your questions.
Hello everyone, and welcome to the webinar. I'm Eduardo Gonzalez from SkyMind, and I'm joined by Arash Mahdavi from AnyLogic. Today's webinar is about using deep reinforcement learning with AnyLogic using Pathmind, which is our cloud-based automated reinforcement learning platform that we've been working on and are excited to share with you today. First, I'd like to go into a little bit of how this webinar is going to be structured. First, I'll talk about why you should look into adding reinforcement learning to your models in the first place. Then, I'll show you how reinforcement learning works, which should solidify the concepts and hopefully give you some ideas of how you can leverage RL. And finally, I'll show you what we have in Pathmind to help you get started and create what I think is going to be the next generation in simulation-based solutions. So first, so you all know that AnyLogic comes with an optimization system, the optimization experiments. This is a powerful system for using a simulation model to help find values that are optimal for the model you have. So, for example, it'll help you ask the question, is 3 racks enough for this factory, or does it need 5? You know, this type of optimization does not go away when using reinforcement learning, so you definitely want to keep it into your toolbox. In the traffic light phases optimization example that comes with AnyLogic, you'll see something that I think is very interesting. If you run the simulation, you can see that there's these sliders that allow you to change the phase time for each light. Now, it also comes with an optimization experiment, so when you use it, you can see this other window on the right, which helps you find the values for the sliders that are most optimal at minimizing the objective here, which is the wait time of the cars. But as a human interacting with those sliders in real time while the simulation is running, you might find that you can actually beat the optimized values by just kind of keeping an eye on traffic and, making a certain slider lower or higher to decongest the traffic at that specific moment in time. So in these samples, you've seen models that contain a system that can be dynamically controlled. And whenever you have a system like this, you can use reinforcement learning to create a type of agent, a learning agent. A bit more about that in the next slide. That can learn how to adaptively control that system inside your simulation in a way that optimizes it for a desired business outcome or objective. It's worth noting that this isn't the same as optimization experiments. Unlike those, the result of the RL training is a policy, a kind of black box policy, that is used to determine those adaptive controlled decisions. Because it learns from experience and isn't performing a precise numerical analysis, the model and the goal can be much more loosely defined. So that might sound like magic right now, and I understand that. So let's go into that next phase. Let's talk about what reinforcement learning is and how it works. So reinforcement learning is the general method of essentially training a robot to perform some kind of task within an environment. In essence, it's similar to how you'd train a dog to perform a trick or teach a child how to play a simple game. In the natural world, first you would set up the situation, the environment there, and interpret the actions of the pupil, or the agent here, and then give them feedback as they try to perform the task. And that feedback is the reward. In here you can see three kind of sample reinforcement learning challenges here. On the left you see the mountain car, where the goal is to get to the flag, but the car doesn't have enough power to reach to the top of the hill by just moving forward. It has to learn how to use momentum to get up there. In the middle is a Doom kind of situation that's interesting, how it learns to run forward instead of attacking the enemies. And on the right hand side you see a Minecraft based simulation, which essentially learns how to navigate this simple room to reach the diamond at the end. Now the interesting thing about these two on the middle and the right is that the model learns from raw pixels, not a specific model, and it just goes to show you how powerful reinforcement learning can be when it's able to take thousands of inputs and still provide a meaningful set of actions. So now I want to mention how this relates to machine learning. Most of what I'd call traditional machine learning is what is called supervised learning. It's where you give the algorithm an input and compare it to the desired answer. There's also unsupervised learning. In unsupervised learning, you don't give the algorithm the answer, but instead you have it detect some kind of pattern in the inputs. Now reinforcement learning is somewhere in between these two. You provide it a reward, but it might not increase for a specific input or action. The algorithm has to learn the pattern that links its actions to the reward it's trying to maximize. If that sounds more difficult, that's because it is. There's a joke in the AI community that RL researchers scoff at deep learning researchers because deep learning is so easy in comparison. Now, while it's difficult, it's not impossible. So recently there have been some algorithms that have been very successful at doing reinforcement learning. One example of very powerful reinforcement learning algorithms that you may have heard of is AlphaGo, which was the only Go bot to be a world champion at Go. AlphaGo learned from logs of ancient Go games, and after they created AlphaGo, they created AlphaZero, which was pretty much AlphaGo, but instead of learning from those ancient logs, it learned from scratch, using mainly self-play against a weaker version or an older version of itself. This version was so strong that it beat AlphaGo 100-0, and the algorithm itself was so generic that it's pretty easy to also have it learn how to play shogi and chess. I would say that a large component of AlphaZero's strength is the fact that it essentially has unlimited data thanks to the self-play. Having enough data has always been a problem with deep learning, but when you use self-play or simulation, you can generate an infinite amount of it. Now, reinforcement learning algorithms aren't limited to board games with perfect knowledge like Go or chess. OpenAI was able to beat professional human players at a highly complex game called Dota 2. To achieve this, the agents needed to learn strategy and cooperation because it's a highly dynamic environment. The neural network for each agent is shown on the right-hand side, and I'm still amazed that they were able to train it because that neural network is so huge. The secret, I would say, to OpenAI's success here is mostly brute force. So while it did beat professional players, you could also say that OpenAI had an unfair time advantage, as it took their AI system 180 years with 256 GPUs and 128,000 CPU cores to reach the same level of play that professional players gain in about 2, maybe 3. So Pathmind puts those same tools that OpenAI used in your hands. Not only does it come with the same algorithms to use to train this OpenAI bot, which is PPO, if I recall correctly, but Pathmind also gives you access to this on-demand parallel compute cluster that you can use to simulate hundreds of years worth of experience across many machines. So with Pathmind, you use AnyLogic as the environment. You simply model the system you want to optimize, and then use the Pathmind helper library palette item to attach the learning agent to your model. Then you import the model into Pathmind, and it will create a distributed compute cluster for you in the cloud for the training. And once you have that, you run dozens of experiments with different algorithms and configurations. And after doing all this training, you get a scoreboard. Once you can select the highest performing model in the scoreboard, or the learned agents policy rather, and export those learning agents policy files and import them back into AnyLogic, so you can see how that agent would respond to different situations, or you can use it to help your customers make better decisions. That's the main workflow. So up until now, I've been talking about very high level, very high and conceptual level type of topics here. But we would like to show you how easy it is to get started with reinforcement learning in a real simulation. So for that, we're going to use this call center model. I'm going to let Arash explain to you the details. So take it away, Arash.
Thank you, Eduardo. Before I start explaining this model, it is important to first discuss how AnyLogic can help us to build training environments representing real business problems. Eduardo showed us some of the interesting examples of reinforcement learning, but most of them were done in games or toy environments. As you see in this Wired magazine excerpt, with all these successes, DeepMind has yet to find any large-scale commercial applications of deep reinforcement learning. As we know, reinforcement learning needs environments which could be real physical environments or simulated versions of those systems. Simulation models naturally provide powerful and realistic virtual environments that enable risk-free training and testing of learning agents. For the training environment, we used a modified version of the interconnected call centers example, which we took from the AnyLogic repository of example models and modified it here. In these examples, we have 5 call centers, and calls are made to each of these 5 interconnected call centers. We use a fully connected network here, meaning each call center is connected to the other 4. So you can see like this one is connected to the rest of the call centers. And each one of them, each call center is represented by a circle, and it has an index that shows the index of that specific call center. If no operator is available to answer the call is placed in the queue. If the queue is full, the center attempts to route the call to another center. For example, here we have some incoming calls. If we cannot process them locally here, we attempt to reroute it to the other call centers. If there is another center that is able to take the call and there is available capacity in the link to that center, the call is transferred. Otherwise, the call is discarded. And this model uses a multi-method approach where each call center is an agent, and inside each agent we have a process. So I can, for example, go inside this call center and see the process that is happening inside the specific node. And we have some visual representation of the output. For example, I can click on each call center and see the operators and their utilization at that point and so on. We are not going to show how this model was built and all of its details, but I need to give you an overview of its inner working so that you have a clear understanding of how reinforcement learning can help us improve its operation. I'm also going to describe in great detail how we added the reinforcement learning functions to this standard simulation model so that the learning agent can see its state, take action, and receive a feedback in order to learn how to best control the model. Okay, so let's take a look at this model in the development environment of AnyLogic. As you can see, we have 4 agent types here. Main is the main agent type, and we have 3 custom agent types here. Let's start with the call. As you can see, this one is a very simple agent type with 3 parameters in it that tells us what is the original or origin call center for this call, the color of it, and the time it entered the system. Then we have a link agent type, and the link is defined to have a capacity. It basically sets a capacity between each 2 call centers in the model. Link capacity specifies the maximum number of diverted calls that can be simultaneously processed between 2 connected call centers. By doing this, we wanted to put a cap on the number of active calls that are being diverted between any 2 connected call centers. Okay, so these are the 2 agent types that define the call and the link, and the call center agent type is the main type that the majority of the logic and everything that is happening and the process that is happening inside each call center is modeled here. Inside each call center, we have 2 types of incoming calls, local and external. Select output, let me zoom here. Select output, as you can see, has some conditions that helps us select the destination of each incoming local call. Let's take a look at these conditions. The first condition in select output finds the destination or current available call center by calling the get first available CC function. Let's find that. So this is the function. As you can see, it is called here. Let's take a look at the function itself. This function, get first available CC, looks into another collection that is called CC index preferences. This is a list of or an ordered list of call centers options that can be assigned as a destination to an incoming local call. The order of this list specifies the destination priority. So in other words, if you look at this, so I'm inside one call center, let's say index 3. Here we have the CC index preferences, and when you run the model, it will be populated by these indexes. As I mentioned, when a call comes in and get to the select output, this function, get first available CC, gets called. And the way it selects the destination of the call is with this kind of logic. To find the destination, get first available CC function loops through the list of call center options. For each item from this prioritized list, we check if it is the current call center and is available. Then we assign it as a destination of the incoming call. So that would be this case. So if it's selected, the one that it looks at is here, like it's 3, and the current call center is 3.2, and we have availability here, it definitely sends it to be a process internally. If the chosen item is another connected call center, let's say the first on the priority list was 2, and it has available capacity in its link, it is selected. If none of the call centers satisfy these conditions, the destination is set to null. Okay, so let's go back to the select output. What happens here is, first it executes this and it returns this a call center. If it's not null, meaning that it can find something, a call center to send this call to, and that available call center equals to this one to itself, it means that I'm going to process it locally. So this condition becomes true and the call gets out of this output. In this else if condition, it says that else if the get first available CC function was able to find another connected call center that has available capacity, select output will divert the call to it. In this case, the call will be sent to the exit block that sends it to the chosen connected call center. So it gets out of this port, goes to this exit block, and here it will be sent to the chosen call center that is recorded in this variable. And going back to the select output, if none of these conditions is true, it gets out of this port, and it will be basically sent to this sync block, meaning that we couldn't find any way to answer this call and we have to drop it. Okay, so now that we learned how an incoming call will be assigned to a call center, let's take a look at the overall process inside each call center. If a call is assigned to be processed locally, it will go through the service block, which is called process call here, and finally goes to the sync process. So it gets to here, it passes through this through port of the select output, it uses the operators. So as you see, this service block is using these operators as its resources, and eventually when the call is processed or answered, it goes to the sync process. If the call center receives an external call, which comes from this enter block, and these calls, it means that this call is diverted and came from another call center. It takes it via this enter block and then seizes one of the available link capacities between the source call center and the current one. So here we seize one of the capacities available in the link between this call center and the call center that diverted the call to us. The call then goes to the service block, similar to a local one. And after it's been answered, it will release the seized link. So when it's done, we check it and we know it's an external call. So we release the link, so the link that we seized here will be released. And then we send it back to the call center that sent or diverted this call to us. And in that call center, it goes back to this location. It goes back from this enter block and it goes through the sync process of the original call center that sent the call. In our reinforcement learning training, the learning agent or the learning algorithm needs to be able to see this environment, or basically get an observation of what is happening at this moment in this environment. And it also needs to be able to take action and change something here. And it should be able to get some feedback from this environment or reward so that it learns something from its interaction. In this specific example, the state of the system is distributed in each node. Like
and that would be what is happening in each call center at the moment, and the state of the links between the call centers. Let's see how we can get part of the observation for the overall system from each node and each link first, and then we assemble all of them into one big array of numbers that tells us what is happening at the overall system. Each call center has a get observation function inside it that tells us the local observation for that specific call center. And it's an array of 8 real numbers, as you can see here, that specify the current state of the call center. The first element here is a flag that tells us whether or not this call center is selected by the learning agent for an intervention in its priority list. The next 4 elements are normalized values of this call center, like calls per hour, operator's capacity, queue capacity, skill level. The last 3 elements are mean utilization of operators, current ratio of busy operators, and current ratio of used queue capacity. So basically, each call center has these 8 elements that tells us, with these 8 elements we can tell what is happening in this call center. These 8 numbers tells us the current state of the call center, and we are going to have 5 of these 8 numbers for each call center. The next one is a local get observation function inside each link. It is an array of 3 real numbers that specify the normalized capacity of the link, its mean utilization, and its current ratio of busy lines. So 3 numbers, we have 10 links, and because of that we will have 30 of these numbers, 3 for each link. And finally, we need to compose all of these informations into one big array that has 70 elements, and this is the array that the learning agent sees. It doesn't have access to these local ones. We use them for ourselves to compose this big array and send it to, or let the learning agent to see it. It has 40 elements from call centers, 5 for 5 call centers, 8 elements each, so 40 elements here. It also has 30 elements from the link. For a fully connected network with 5 nodes, we have 10 links, and you can calculate it by this formula: n multiplied by n minus 1 divided by 2, and n is the number of nodes. And so we have 3 elements in each link, so 3 multiplied by 10 becomes 30. So in general, in total, we will have 70 elements in our global observation array, and this global observation is the one that is used in the training. The next function that we wrote for the environment is called DOACTION, and that function lets the learning agent to make changes to the environment. In each step, the learning agent has 125 different actions to choose from. The learning agent makes its choice by selecting a number between 0 to 124, with each of them corresponding to one of the possible actions in the action space. If it selects a number between 0 to 4, it means that it is selecting a call center to possibly change its call routing priority in a following step. If it selects a value between 5 to 124, it means it wants to change the routing priority of the previously chosen call center. All permutations of 5 choices are mapped to keys that start from 5 to 124. Basically, each key returns a specific priority order from all possible permutations. The reason behind choosing to do the intervention in 2 separate learning steps is to reduce the action space. In this scenario, the action space is 5 plus 5 factorial, which equals to 125 possible action choices. If we had chosen to have the selection and intervention in one step, the action space would have had 5 multiplied by 5 factorial, or 600 possible action choices, which made the learning process harder. And finally, we need to calculate the reward that the learning agent gets in each step. The reward, similar to the get observation, is gathered from the rewards that we get at each call center. So if you go inside a call center, you see this local get reward function, and this function basically looks like this. If no call has been answered yet, return 0, so the reward will be 0 for that step, or return a negative reward between -1 and 0, that is the ratio of bug calls to the summation of answered calls that are local, external, and number of bulk calls. So this would be the reward for this call center. And if you go to main, you get this global reward function, which is a summation of all the rewards from the 5 call centers. It's a loop that loops through them and adds them all to one reward function. One important bit is, and Eduardo is going to show you this Pathmind helper in the next step. But when you pass, if you click on the Pathmind helper, which is the link between the Pathmind platform and your AnyLogic model, it has an observation for reward field. If you want to send some information to the Pathmind platform and calculate the reward there, you can do that by building an array of all the numbers needed for the rewards calculation. That array of doubles should be passed in the observation for reward field of Pathmind helper. In this particular example, we already calculated the reward value, and so we just pass it as a one-dimensional array that has the reward in its first element. So here we already summed all the rewards, and we pass the reward directly as one value that is inside this array. But because this field only accepts an array of elements, we built a one-dimensional array with just one element, which is the total reward for each step. Now that we know how this network of interconnected call centers work, let's think about what is that we want to learn with this reinforcement learning, and what is the use of the policy that we can learn from it. From the perspective of the overall system, this is a distributed business. So we have different call centers at different locations, and each one of them has some capacities and attributes. For example, we might have 20 operators here, 10 here, and so on and so forth. And because we wanted to utilize all of our resources, we added this mechanism that if a call comes in, we cannot process it internally, we can divert it to another call center that is connected to this one. And in this case, it's a fully connected network, so each call center has access to all the other call centers. Okay, but for this thing to work at its best, each call center has to have a meaningful priority list. And that is what, when I go inside this, you see that each of these call centers has this index preferences collection that tells us what is the current priority. And depending on how you order this list, it's going to affect the overall performance of the entire system. And for us to measure how this overall system perform, we looked into like how many calls we cannot answer properly, and that would be something that we built into the reward function. If this reinforcement learning agent or the learning agent is successful, it will figure out a policy that can dynamically change the order of routing mechanism in each of these call centers to minimize the number of bulk calls in the overall system. And if it learns that, then it has this kind of dynamic, adaptive policy that can tell us what is the best way to manage this entire operation. So now we go back to Eduardo, and he will talks about how Pathmind platform can be used to train a policy based on this environment.
Okay, thank you, Arash, for that explanation. Hopefully everybody now has a good understanding of the model and the challenge that it's kind of presenting here, where you want to minimize the operators you have on call, saving money, but you also want to minimize the number of disappointed customers. So there's two conflicting goals here, and this is kind of the perfect type of problem that using reinforcement learning can optimize for. So let's see how to do some reinforcement learning on this thing. So the first step to using Pathmind is to install the Pathmind policy palette library. To do that, you simply click on the plus icon on the bottom left of the palette tab, then select the Pathmind policy library that you can download from pathmind.com. Next, select the new Pathmind tab and drag a Pathmind helper onto your main agent in your model. Once you've added a Pathmind helper to the model, you can access its properties to see the various functions and values that you have to define to hook it up to your model for training. The first function to define is what we call the observation for training function. It does the job of the interpreter in the visual that you saw earlier and I have highlighted here. And it has to take the data from the model and turn it into an array of real valued numbers, which is the language of neural networks. The learning agent will see these values and nothing else. So it's important in general that it should contain all the data you think the agent will need to perform its job optimally. In the call center model, the observation is simply an array of the various things happening in the model, like calls per hour, operator capacity, and the number of queued calls. Now, the data for calculating the reward can use a different set of observations, but like the observation for training function, should also be an array because it will be stored for the training process. Next, you have to implement the DOACTION function. The function's job is to take the action that the agent has chosen and actually perform it on the model. An action is just a number from 0 to the number of possible actions, and you're in charge of how big that number is. You can think of it as the agent telling the model which button it wants it to press. Now, in the call center model, at each time step, the action is to either select a call center for intervention or update the priority list of the call center that was selected previously. Now, this is implemented by simply calling the various functions defined on your model. One thing to note, which is something we actually ran into with the call center model, is that the agent will have trouble learning if there's a huge number of actions. So it's always best to have the smallest number of actions possible. In the call center model, we actually separated the action space into two so that it can either select a call center for intervention or it can change the priority. It can't do both at the same time. The next few steps are done in Pathmind. So before you do that, first export your model into a standalone Java application and then zip up the model file and the database file if you need. Next, log into Pathmind in your browser and then upload the zip file as a new project. And Pathmind will inspect the zip file for correctness, and if there's no problems, it'll move you on to the next screen. Next, you'll be able to define the reward function. The function will receive the result of the 4 reward versions of the getObservation function taken from 2 points, one before the DOACTION function runs and one after the DOACTION function runs. It's the job of the programmer here to define a function that determines the reward value from the after observations or by calculating some difference between the before and after observations. And which one is best really depends on the model you're doing. On the screen, you can see the reward function that we used for the call center model. It's defined as the sum over all call centers of the inverse ratio of bulked calls over the total number of calls. The total number being the n answered local plus n answered external plus n bulked here. Other than that simple if statement at the top to prevent the division by zero error at the start of the simulation, it's just a simple and pure mathematical function. Now, an action might not have an immediate change in the reward, but that's typically okay because the algorithms that we use will typically batch these observations and reward values into what's called experience replays, so that it can learn that certain actions are good even when there's a significant lag between the action and the reward. Likewise, a good reward function should also always try to return a non-zero value so that there's a lot of signal, as they say, for learning. An example of an alternative reward function we could have used for the call center would be one that simply returns a 1 when a customer call finishes, a -1 when the call bulks, and a 0 otherwise. But this one would have been more difficult to learn from because it would have been full of zeros and therefore much harder to learn. And once you've finished defining the reward function, you just click the quick run to debug the reward function and make sure that it's doing what you think it should do, which you can see in the next slide. Now you can debug the reward function by doing what's called a quick run. There's a quick run button there. And this will run the training for a short amount of time and show you a graph of the reward function value during the training run. The reward function graph tells you how well the agent is learning. Now, since the idea of the quick run is to just debug the reward function, so you shouldn't expect it to learn very well. But you can check that it's not flat or causing any exceptions during the training or being incredibly spiky for some reason that you're not sure of. Once you're happy with the reward function and you're pretty sure that it's working great, you can perform a discovery run by pressing that button. And this will spin up a cluster of nodes and run tens to hundreds of training simulations that use different types of algorithms, neural networks, and other hyperparameters. Now, I think this part is Pathmind's most important feature. You don't have to be an RL or deep learning expert. Pathmind combines our data science know-how and a fair amount of brute force so that you can spend your time focused on your model. Now, as training finishes for each simulation, it will collect the various scores into the scoreboard. And depending on your model, you should see some pretty high scores, but also some low scores. After the discovery run is complete and you have all the trained policies from the discovery run, you can select one or a few of the top experiments and then train them for just a longer amount of time so that you can give that learning agent more experience and hopefully a better score. Once you're finished training, you can export the brains of that agent, what we call the policy, and incorporate that into your model. So pretty much you just give it a name and click export and you'll get a zip file that contains everything it needs to run the trained policy inside of AnyLogic. Now, looking inside, you can see that it contains a trained TensorFlow neural network file and some metadata that's used to help keep track of it. To use it in your simulation, simply place that zip file into your projects folder and specify the name of the zip file in your Pathmind helper and enable the policy. Now, this should work just as well when you export the simulation to a standalone Java application. You can distribute this to your customers directly. An alternative is you can also extract the PB file and the variables and use it inside of a server outside of AnyLogic. The model files are typically fairly large, so I wouldn't in general expect them to be runnable inside an Arduino or other kind of real-time AR chip. But a PC or a Raspberry Pi, anything capable of running Java or Python should be able to run the TensorFlow model to control systems in the real world. So finally, let's talk about results. Here you can see the results of the traffic light example. While I understand how simple this example is, it's also incredibly easy to understand. So on the left is a traditionally optimized phase duration, and on the right-hand side is the same traffic light but with the phase durations controlled by a learning agent that has been trained by Pathmind. Here we are showing a challenging situation which you can see on the top left, where the blue north and south road is almost completely empty in the morning, but has this huge rush hour in the afternoon. The learning agent is able to respond to that situation in a way that reduces the wait time of the cars. In the end, it achieves a 50% more throughput without adding any new lanes or anything like that. And so I think that's pretty good. And while this is a simple model, it learned by itself by interacting with the model and without any tuned heuristics or hand-tuned heuristics, and in about an hour. So that means it's easy for us to scale it up to a more complicated set of traffic lights by just adding more compute power, and that's the real promise of RL here. So that's pretty much how you add reinforcement learning to your model, and hopefully you have a good idea of what Pathmind can do for you, and you might be interested in checking it out. And luckily, we have prepared 2 models that you can use to try everything, so just to see the detail of how everything works. Now, the traffic light one is a great place to get started with to learn the basics. It's a very simple model. And the call center one, which we were showing here, is better to see how to deal with things like how to optimize a huge action space. Now, to get started, just head over to pathmind.com and sign up to get access to the private beta. We'll be rolling out access weekly and scale it up as we gain confidence in our system meeting the compute demands of everybody training large policies. After the beta, we'll have a simple 2-tier pricing model. One that's a prepaid thing limited by a budget, and an enterprise one that allows you to get access to the compute power you need without having to worry about any quotas or anything like that. And so thanks for your attention during this webinar, and I hope you're excited to try it out. We'll open it up for questions now, but if you have, if we can't get to your question or you want to ask, talk more about Pathmind or learn more about it, feel free to email us at the address on your screen.
At this point, Eduardo is joining us for the Q&A session. Let's wait for him so that he joins us. And by the way, so you asked a lot of questions, and Tyler helped me to assemble a list of questions. I'm going to start by answering some of these questions, and hopefully Eduardo will be able to join us. So the first question that is related to AnyLogic is, what was the use of the links in the model? And basically in AnyLogic, when you're using links and like connections, in most cases, you're using it for message passing. This model was a little bit different. We wanted to have some form of capacity in the links, and that's why so the model has a agent type for the links, and inside that agent type, you have a resource pool that specifies how many units or entities can be inside that link. So it's a kind of custom built link to put some form of cap on the number of units that can be simultaneously between 2 points, in this case 2 call centers. And it was a 2-way connection, so that was the point for having a link in this model. So it's definitely going to affect how many calls can be in between 2 call centers. So the second question is, so I'm still waiting. I think Eduardo joined us.
Yep,
okay.
I'm here.
Okay, perfect. So I think this question, Eduardo, goes to you. The question is, can I change the reward function from inside Pathmind?
Right, so that is a good question. So in Pathmind, you export your AnyLogic model and import it into Pathmind. And inside of Pathmind, you will have a section where you can edit the reward function. Now, inside that that text area, you essentially have all the power of Java and all of your agents available to you. So you can actually write as complicated logic as you want in that system over there. And when you are kind of debugging your reward function, it's totally possible to change it, do a test run, go back and change it some more, do a discovery run,
but also think maybe I should have something else in my reward function and go back and change that as well. So you can implement as much as you want inside of AnyLogic, or you can kind of leave that for that Pathmind area, and then you can kind of customize it to your heart's content.
Okay, perfect. So I have a quick follow-up question on that. So if we have if we specify multiple reward function, does Pathmind keep track of all the previous runs for those reward functions?
Yeah, that's a good question too. So when you change the reward function, the scoreboard becomes incompatible, right? So like those are two different kind of experiments in that sense. So when you do like a discovery run, all of them are using the same reward function, so they should compare to each other. So when you do change it, you're going to have a kind of fork it off into another system, and you can create as many forks as you want.
Okay, perfect. So the next one is also I think you can answer it better than me. It's a simple question. I actually have it on the screen. How can I access Pathmind? So by going to pathmind.com and registering. But is it open to public now, or how?
It is not. So we're currently getting ready for a public or a kind of private beta, as they would say, and we're going to kind of do the release little by little. And the first people who start registering now will get access to it within the next month or so. And probably we'll start kind of rolling these things out in a week or two for people to start getting started.
I'm going to make sure that I register right after the webinar.
Yes.
Okay. Okay, so this question is, I can answer that, and Eduardo, please add to what I'm saying. How did you add the policy to the model? So the helper object of Pathmind has a section in it that when you download the zip file, which is the train policy, you can select an option there and say, I wanted to use the policy, and then there is a browse functionality that lets you to select the zip file. And if you run the model after that, it uses that policy to control the model. I think you need to add an event to actually call that policy in some intervals too, but I think that should be it, right? Am I right?
Right. So when you add the helper, if you look at the properties page, near the top is an is enabled checkbox. And so when you want to use the policy in your simulation, as opposed to only training, you check that checkbox to enable it, and then you can specify the file name of the policy you want to do inside of the helper properties.
Okay, perfect. So I think we have one more question, and that is for me. Do I need AnyLogic Professional to be able to use Pathmind? So as you know, AnyLogic has 3 versions. So it has Personal Learning Edition, which is free. It has researcher license for research, and it has professional license. So for this specific use case, you need to have professional license because it uses the exported model, and that functionality only is available in AnyLogic Professional. But for some of you who are interested to learn more about the Pathmind and you want to use that platform, we are going to give you access to the exported models, like the model that you saw in this webinar will be available. You won't be able to change it or edit it, but if you wanted to try this platform, Pathmind platform, we will provide several exported models. So you can get an idea if you were able to export your model, how that's going to work, and you can test the workflow of Pathmind and learn some policies from there. And what I have on the screen is some of the upcoming training events of AnyLogic around the globe. Just to clarify, these are standard AnyLogic trainings, so they are not about reinforcement learning or those connections. It's for you to learn how to build simulation models as environments. Eduardo, is there anything else that you wanted to say before we wrap up the webinar?
Yeah, so one other kind of thing that we kind of talked about in the briefly in there is the ability to export the model and use it outside of AnyLogic as well. And so I think that's a really interesting use case, and there's it's pretty easy to use that model in a Python script or a Java application using DL4J. So if if you have a use case where that might be useful, feel free to check it out and let us know if you try it, so that we can help you get up to speed.
Okay, perfect. Thank you so much. And thank you very much for all of you for joining this webinar. On behalf of AnyLogic company and AnyLogic users, I want to thank you, SkyMind, for giving us this fantastic platform. It adds a new dimension to what we do with AnyLogic, and it simplifies the process a lot. So for us who may not be RL experts, we can use this platform and get access to all the new algorithms and all the pretty cutting edge algorithms in reinforcement learning and use them in conjunction with AnyLogic. So thank you again for all of you. Thank you, Eduardo and the SkyMind team. We are, as I mentioned, we are going to post this webinar on our website, the video recording and all the material that you need and all the links. And we are going to send you a survey to get your feedback. We appreciate that. And I think that's it. And thank you, and have a great rest of your week. Thank you.
Thanks, everyone.